have decided to entitle my talk Keeping the Process Window Alive. Process window, I mean the bound of the plume characteristic in which we produce good coating, which is the holy grail of any manager of booth, ensuring that the booth produces a plume which leads to good coating. Like we have seen since this webinar, this is a material science problem. And so at Tecnar, we produce sensor. That arrange sensor you see on that slide is the fourth generation of a captor of a sensor that we call Acura Spray. And it measures the various properties of the plume in terms of its temperature, intensity, velocity, and several other characteristics of the plume. This sensor is existing for the last 15 to 20 years, and it has now reached version able to measure plasma processes, HVOF processes, and HVAF processes. But of course, data comes not only from that sensor, but also from the laboratory. It also comes from the booth parameters. And we thought at Tecnar it would be important to build a platform that we call the hub, in which all this data would be collected at one place, and in which we could build some intelligence in order to assist the material scientists into developing good coatings. So of course, like we have seen, the demands in the coatings keeps climbing. It's an industry which is developing greatly nowadays. Of course, like in every industry sector, there is a huge challenges because the old people, the ones which have been developing this sense by hearing the jet that the coating will be bad, those old timer guys are going to retire, and replacing them with young experts is becoming harder and harder. And so there is a drive to automate this process. We of course need to scale the production without losing the coating quality. And of course the know-how from the human expertise, which is to be preserved. So here we have a beautiful picture of a plasma spray. It is spraying an aerospace part. And what the Acura Spray, our sensor at Tecnar, is doing is periodically monitoring this plume, ensuring that the coating, or at least the characteristic of the plume, will remain identical. This identical comes from the fact that there is a general consensus that if the characteristic of the plume remain identical, we could prospect that the coating property will also become identical. So all we have then to do is to find the right window of process, the right range of temperature, intensity, or velocities of those particles that leads us to interesting coating properties and maintaining this normal plume characteristic. So let us see how we do this. Here, it's an illustration of a spray being measured using our Acura Spray 4.0. We see a video, an image of the plume. We can see that we analyze at a given distance from the jet the width of that plume and its various characteristics in terms of temperature, velocity, intensity, and so on. You see here that this is a plasma spray, and today I will be going through a year of a collection of data from an HVOF process. It doesn't matter, this is a very analog rational. And so let us dive into this year of collecting data from HVOF production booth. And then we could all take the role of a manager of a booth and ensure that we can guarantee the repeatability of this characteristic throughout the year. Of course, our hub needs to know from what we call recipe is this process. There is various powder, there is various ways we can set up a booth in order to get the coating that we desire. So our hub obviously proposes a way to ingest your recipe in terms of its various characteristics, the gas, the pressure, and so on, the current, and so on. And then we can certainly capture and ingest. Here you see the whole year from the months of May 2024 to July 2025. And you see that throughout the months, we've been ingesting runs, and each point there represents a spray. You can see here two axes, the temperature and the velocity. And the red line, the dashed red line, are the bound that has been set by the industry, at least at that particular booth. And that bound there is being defined by taking a bit of margin around that normal state. And this has been done by various ways, usually involving mechanical properties, mechanical characterization of the coupon. And what the hub is trying to build as an intelligence is an automation of this definition of the normal state. So let us see how we go and do that. So first of all, there is a process of training a window. What we are going to be doing is learning what's the fences of your normal run. How is your normal looking like? And we do not need any bad coding to do that. All we need to do is that we continue running your booth as best as you can, continuing regular maintenance, periodically taking some coupon like the way you do. And all we have to then expect is that the hub is looking at your normal and defining it. So we do that through a process that I will not describe today, but this is involving machine learning, in which we reduce the dimensionality of the space, and we can define stability criteria, look at how your various run looks. Some runs will be far from the normality, some run will be close to the normality, and eventually we can provide to you a bound, minimum and maximum velocity that we have seen over the course of the training period. This radial chart that you see on the left shows you the various features. We call feature, intensity is one feature, velocity is another feature. And the blue zone that you see here, it's a zone that we have seen often well known as like twice the standard deviation of my distribution, 2 sigma. People tend to like to define this. I will make the average of my runs and take a 2 sigma around, and this should be telling me what's the average. This is a conventional way of doing so. What we go in our hub is one step further. We are operating into a complex space in which we can look at this cloud of run moving and evolving in terms of their compactness and position in that space. And what you end up with is a hub proposing you with a model window. For each of these features, they are representing there in orange, and the silver ones are your window. So you see that your window usually is much wider because you tend to, take a bit of margin from your normal state. And the other observation that you can make is that your normal, the orange, is not necessarily centered on your industry window. So that's two interesting things. Of course, now you have to trust the window that the hub is telling you. So there is a process to do so. And this process, you all know it. You all wonder whether or not that orange window proposed by the hub is providing you good coding. So you could test this by ingesting your lab result. So to give you a concrete number, over the course of the year, we've been ingesting about 320 runs. Out of those 320 runs, we had about 90 coupons. So throughout this year, we could gather coupon property in terms of their porosity, oxide content, coating thickness, tensile breakdown, and so on. And then what we could then do is take some runs, which are the orange ones on the left figure, runs which are very close to the normal, at the center of that cloud. And we could also fetch some runs which are far from the normality, the green ones. and then look at their mechanical property. So here I've just shown you 3 mechanical properties. The first one is the particle size. You can see that as we go close to the normality, the particle size tend to be slightly lower, which is a good sign, at least in some process, of course. The contamination tend to have been decreasing when we are closer to the normal. And last but not least, the bond strength is slightly higher. So this is interesting because you now know that within this orange zone that the hub is telling you, you have a good sense that you can obtain mechanical property that are within the range of interest. Of course, here in this slide, I have not shown what's the maximum and minimum particle size accepted for that coating, but that's just an illustration of one way you can start building trust on your process. There is a second thing you could do very easily, is adjust the oxy-fuel ratio for that particular process. We all know that fine-tuning that ratio is about playing on the gas bottle, and a slight adjustment on the knob may affect the oxy-fuel ratio a little amount. And it's very important to get a feel on how much this will affect the plum characteristic. In this particular slide, we can see the oxy-fuel ratio has varied a little bit. Some of the features did not get affected at all. The plume angle, the plume deviation did not get affected. However, as the oxy-fuel ratio increased, the velocity has tended to lower as well. And you can see the width also quite affected. So this is just 2 illustrations of how you can trust that window that is provided there by the hub automatically by this machine learning process. Now that window, how do we use it? And more important, how do we keep it alive throughout the year? So here is a chart. Again, the x-axis is the year, the time. We see the same months from the May to June to July. And on the y-axis is the number of runs that were ingested every week or every couple of days. You can see that some period of the year we've ingested lots of runs, some period of the year we've ingested a little less runs. But what's important to see here is that for the first couple of months, we were into a period of training, and then the stability criteria has been reached, and we've been providing to you a first window of process that we believe it to be your normal. We locked that window and we call it the core. And then you continue your process. Months passes, more runs get ingested by the hub. And then we continue looking at how this cloud is moving throughout the year. In February there, I've illustrated this with a white dashed line. In February, a maintenance on that boost has been performed. And this maintenance, we all know, they can affect positively or negatively the boost. And then automatically, it was important to monitor whether or not our cloud of runs has moved away. And we call this a drift. And so as this maintenance has been occurring, a drift has been detected by a criteria that I will not develop today. But this candidate now is proposed to you as a replacement of that core initially trained about a year ago. How this is illustrated to you, the same way we looked at it earlier. We see where we used to be a year ago in orange, and it tells you also now you are there in green. You can see in that particular cases, we are slightly hotter. We are also slightly slower in terms of the velocity. And more important, we seem to be tighter in every of these features, indicating that possibly this maintenance has cleaned the deviation observed in the various features. This is an interesting observation, and so we could decide to override that initial core dating back from 1 year and working from now on with this new representation of the normality of that boost. So what do we do then, thanks to this hub? Many of you that have been using the Accuraspray 4.0 is aware that the challenge is to set that boundary between this orange and red state, the red state being where we produce bad coating. In order to define that red boundary, a huge number of coupons is necessary in order to target what's the minimum temperature, velocity, intensity, and all these features, and what's the maximum for all of these features. This is something that we are well aware is quite expensive to do in reality. And so what we propose is to replace this by a tight observation of your normal state, which is this green zone. And so now we propose to look at this green zone and define this window of process provided by the hub as the boundary between the green and the yellow zone. Of course, you always have to be worried about your danger zone, but now not as before, because we provide to you a granularity within this large area between these two mean and max red zone. How do we do this in reality in our hub? A manager can do this easily. He has been prompted by the hub, its web-based platform, that a new candidate is ready to replace. What the manager will do, he will first select which of these booths is concerned by it. That's what we see on the top left corner. What controller, what Acura 4.0 do I want to push this new window into? Within each of these controllers, we might have at step 2 different recipe operating. One booth often operates with multiple powder. So we select what recipe we want to push this into. Then in the step 3, we review the changes. We decided on that particular example not to change the red boundary, however, make a small adjustment of what my normal state is. You can see it's slightly hotter in temperature, slightly slower in velocity, and the intensity here being slightly tighter. And finally, you can review what you are about to do, which is overriding the process window at a distance in a controller which is located on your site or remotely on a booth that you manage, thanks to the network of your own industry. And finally, you decide to push this, and you have a callback from your controller validating that you've indeed overridden and now operate using this new window of process. So finally, in conclusion, what we've been trying to do here at Tecnar is provide to you with a complete solution of sensor, which are capturing your booth, an intelligence, which is training on your normal state. Of course, we need you to trust the window that we will be doing by applying normal and act that you already do, which is periodic coupon property. And then the platform will be watching your normal operating over the year and potentially detect drift. When this drift is detected, you are being prompted and you can decide in one click to make that new window evolve. That's why we talk about windows staying alive. And we try to propose this solution without you needing additional machine learning expertise, because once again, like I have started to talk about, the problem of thermal spray is more of a material science problem. And at Tecnar, what we try to do is to provide you with all the necessary environment or ecosystem such that you can focus on that particular aspect of material science. So I think I have said what I wanted to say. And once again, with this new platform, we can valorize the data that you already collect without changing or disrupting your flow. Thank you very much.